Welcome to my channel. In this problem, we are given a block of mass m and it's moved up a hill by applying a constant force F, which is always tangential to the curvature at that point. So if we take this point, if we draw a tangent at this point, F is parallel to the tangent. Okay, it's tangential to the surface at every point, and there exists a friction between the block and the hill, and the coefficient of friction is mu, and there's an obvious gravity force acting down. So what we are required to find, and the dimensions of the hill is given, alright, and what we are required to find in this problem is the work done by the force while moving the block from here to here. Alright, this may seem weird, okay, because it's just a random hill. The hill can be of any shape, so you might think, is it really possible? Well, it's possible. This is in fact a very good problem. That's why I'm writing the solution here. Alright, so let's solve this problem. So let's think, what are the forces acting on this block here? So well, there's a constant force F, there's a frictional force, and there's a gravitational force mg, and these two are constant. Well, this varies, and we'll see how it varies now. Alright, and now let's think about the work energy theorem now, because I'm sorry, I forgot to mention this, and it's given that the block is moved slowly, and what that means is the velocity here will be the velocity here. So the block's velocity at each instant will be 0. Okay, this seems absurd, but it's negligible. Okay, it moved very slowly. Okay, it moved very slowly up. So there's no change in kinetic energy between the first position and the last position. So now let's think of the work energy theorem. So now we know, according to the work energy theorem, that the work done by all forces is equal to the change in kinetic energy of the block. So here the work done by force plus work done by friction plus work done by the gravity, okay, equals 0, because there's no change in velocity, and so there's no change in kinetic energy. We know what's the work done by gravity, right? Because the work done by gravity is just minus mg. Here minus represents the negative direction because gravity acts here, whereas the displacement is h to the top, right? The block starts here but moves a distance h above the ground, okay, opposite to the direction of gravity. So hence we get a negative sign, a negative work is done. So minus mg times h, and just minus mg h, and you just substitute back here, we get work done by friction plus work done by the work done by force plus work done by friction is mgh. Okay, we just transpose the minus mgh to that side. Alright, so now it seems that if we can find work done by friction, we can find work done by the force F, which we are required to find. Alright, let's try to find the work done by friction. Okay, we know that the block is moving at all times, so the value of friction is always the limiting value, right? And we know the limiting value of friction, F max, is mu times the normal force. Okay, so now we need to find the normal force. And now if you look at the diagram carefully, we drew this, right? We drew this tangent at some location. Let this tangent make an angle theta with the horizontal, right? Let's just move the diagram here, making an angle theta. Let's say the mass m. Okay, this is not the exact diagram, I'm just taking at an instant, I'm just taking the angle made by the tangent with the horizontal. Right, at this position, what are the forces acting? You have an mg, you have a frictional force, and you have normal perpendicular to the surface at that point, right? So we resolve the force diagram, we resolve this mg force perpendicular and parallel to the surface. So this is just 90 minus theta, so we get a friction plus mg cos 90 minus theta, which is an mg sin theta, and an mg cos theta here, right? Let me just erase this. Alright, and we know the frictional force is always at its maximum value, right? So yeah, no, we drew this diagram to find the normal force, right? And at every instant there is no net force along this direction, otherwise the ball, this block will move towards the hill, inside the hill, which is weird. Okay, that doesn't happen. So n equal to mg cos theta at every instant, right? And theta here refers to the angle between the tangent at the point of contact with the ground and the horizontal, right? Okay, so f max is just mu n, so it's just mu mg cos theta. Well, we are trying to find the work done by the friction, right? So we know, let's say this body moves a distance some dr. Okay, let's not name it. Okay, let it move some distance here. Okay, I'm representing this by this dark line here. So we can resolve that displacement as in the x component, let's say dx, and the y component dy, right? All right, and now this angle is theta, so even this angle is theta. Okay, by corresponding angles. Okay, these two lines are parallel. And now this is dx, so what will this line be? This displacement, if you just consider this triangle we got here, a right angle triangle, this will be dx by cos theta. It's easy to prove, you can just use some trigonometry, it's easy to prove, right? So if my block moves a small distance up the hill, the work done by friction, okay, we'll call that dw, because it's a differential part. That's an infinitesimally small part of work done by friction, will be the force due to friction at that point, will just be mu mg cos theta referring to this angle, times the small displacement, which is just dx by cos theta, right? And here we need not use the notation f dot s. Indirectly we are using it, but here the force is just parallel to the direction of motion, direction of displacement, and it's in the opposite direction. Notice the friction is always opposite to the direction of displacement of the object, right? In this case it's the opposite, so we get a negative sign there. And notice that the cos theta cancels, giving us minus mu mg dx. And now if we just integrate, right, if the block moves, if dx tends to 0, if x tends to 0, work done with 0, right? And if x tends to here, the block moves a distance L, right, in the horizontal direction. So here the upper limit will be L, right? L. So and the work done is, let it be W. We need to find that, right? Let it be work done by friction, equals minus mu mg, as these are constant, can come out of the integral 0 to L, and integral of dx is just L. That's the same thing we did here, right? So minus mu mg, it'll be x, and you substitute the upper limit, becomes minus mu mg L. So yeah, we found out the work done by friction, and now we just substitute this back into our original work energy theorem equation that was here. Let's just bring this down. Let's just bring it here. Alright, so now we can find work done by friction, and work done by friction, the work done by the force F, work done by friction is minus mu mgl, just substitute here, mgh. So work done by friction is, you just transpose that there, mg h plus mu l. And that is the answer to our problem.